Welcome to another podcast. This episode we're going to be taking a look at a couple of limit laws and how to use those limit laws to find the limit of a function without having to resort to the graph. To get started here, I'm just going to list a few of the more important limit laws and then we'll go from there. So the first one on our list is what's called the constant law. So if you look at the limit as x approaches a of a constant c, then that's just c. Constant functions, their limits are always whatever the constant is. Next up is sometimes called the identity property. And that says if you look at the limit as x goes to a of x, that's equal to a. Next up we have the addition and subtraction property. So if you have two functions that are added and or subtracted together, you take the limit of those, then you can take the limit of each of them separately. So this the limit as x goes to a of f of x plus or minus the limit as x goes to a of g of x. This essentially means that you can distribute the limit. Also, we have a similar property for multiplication and division. If you look at the limit as x goes to a of f of x over g of x, that's the same as the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. And then the multiplication version of that is if you have two functions multiplied together, then you can take the limit of each of them separately and then multiply the limits. The limit of the product is the product of the limits, is basically how you would say it. A tricky one is exponents. So if you have the limit as x goes to a of, let's say, a function raised to the n power, then what you can do in that case is take the limit inside the exponent, x goes to a. You can take the limit inside the exponent, and then do the exponent after the limit's done. And then because we talked about in class, because roots are like exponents, then you can take the limit as x goes to a of, let's say, the nth root of x, or f of x. That's the same thing as bringing the limit inside the root because the root acts like an exponent. So f and g are pretty much the same property. We just have to be careful about one thing. So we get here that this is the limit of f of x. We have to be careful about one thing, and that is if n is even. So if this is an even root, like a square root, a fourth root, sixth root, and so on, then what you have to be careful about here is that the limit as x goes to a of f of x has to be greater than 0. Remember, you can't take square roots of negative numbers. So I need for that limit to be a positive greater than 0 limit in order for this property to apply. Otherwise, you would say either the limit doesn't exist or you'd have to try something else to find the limit. So those are our limit laws. And using those limit laws, we can most of the time pretty easily calculate a few limits. And I want to do a couple of examples here with you. I'm going to start with looking at the limit of a polynomial. So I'm just going to take an arbitrary polynomial and I'm going to ask what is the limit as x approaches 2 of 3x cubed minus 2x plus 4. And so since this is the first time that we're doing this together, I'm going to do this out using all of the limit laws. So the first limit law says we've got things that are added or subtracted here, so I can take the limit to each piece. So we've got the first piece, then it's minus the limit of 2x plus the limit of 4. So this is using property C, that the limit of things that are added or subtracted together, I can take the limit of each piece individually. Then if we look here, the limit as x goes to 2 of 3x cubed. The way that this works is limits can go inside of the scalar and they can go inside the exponent. So this is 3 times, well, let me go ahead and back up. So this is equal to, we've got the limit 3 times x cubed using property E, that's a product. So I can say that's the limit as x goes to 2 of 3 times the limit as x goes to 2 of x cubed minus, I can do the same thing here, the limit is x goes to 2 of 2 times the limit as x goes to 2 of x plus the limit as x goes to 2 of 4. Now I'm ready to evaluate these limits. The limit as x goes to 2 of 3, well 3 is a constant, so if I go by property A, the limit of 3 is just 3. The limit of x cubed as x goes to 2 is, well, the limit by property F jumps inside the power. So I'm looking at the limit as x goes to 2 of x quantity cubed minus the limit as x goes to 2 of 2 is just 2. And then by property B, the limit as x goes to 2 of x is also 2. Just plugging the 2 in for x. Plus, here's the constant property A, limit as x goes to 2 of 4 is just 4. So finally, if I evaluate limit as x goes to 2 is 2, this is 3 times 2 cubed minus 4 plus 4. So altogether, 2 cubed is 8. These cancel. 8 times 3 is 24. So the limit there is 24, and what I want you to see, or what we should see here, is that had I just taken the limit of this polynomial and plugged in the 2. So if I just plug in the 2, you see that we would get the exact same thing. Essentially what I just did there was I said the limit as x goes to 2 of the function f of x is equal to the function evaluated at 2. That's what I did in both cases. Now, they are the same. What turned out to be the case here is that when I calculated this limit, these turned out to be the same thing. Now, this is a very special property when this happens. This is called continuity. So the function is continuous at x equal to 2 when it satisfies that property. We'll talk more about continuity in a future video. But not all functions have that property. Polynomials do. So you can reliably calculate the limit of any polynomial simply by plugging in the limit value and know that you're going to be okay. But let's look at an example where things maybe go a little bit wrong. So this example I'm looking at now is a rational function, so I'm going to look at the limit as x goes to 2 in this case of x squared plus x minus 6 over x minus 2. Now if I use property D, then the limit of the quotient is the quotient of the limits, so x goes to 2 of x squared plus x minus 6 on top, and the limit as x goes to 2 of x minus 2 in the bottom. And so you see in the top we would get 4, so this is a polynomial in the top, so we can just directly plug it in. So in the top we get 0, and in the bottom we also get 0. So in both cases we get 0 top and bottom, and we might be inclined to say that that does not exist because this is what we call indeterminate, meaning that there's nothing to come out of that. So we went wrong here because we tried to plug in 2 when the bottom is discontinuous at the value x equal to 2. So instead what I have to do here is, if I look at it real quickly, what's going on is the numerator, x squared plus x minus 6, actually factors into x plus 3, x minus 2, and the bottom is x minus 2, and therefore algebraically I can cancel the x minus 2, which basically is removing the bad point x equal to 2 from the problem, And then what I'm left with is the limit is x goes to 2 of x plus 3. Plugging in 2 then, that limit is 5. And so the actual limit for this function is 5, even though if I just tried to plug things in directly, I would get 0 over 0, which is an indeterminate answer. So the point is, some functions have this nice property that you can just plug in the value of x in the limit to the function and get the answer, like we did here with f of 2. But down here, doing that leads to an answer that's wrong, when in fact the correct answer is obtained by removing the discontinuous point at x equal to 2. We call this a removable singularity when this happens. And so the point x equal to 2 is a removable singularity or a discontinuous point for this particular example. Now we're going to do some more of these in class, but I just wanted you to see that sometimes you can just go ahead and plug them in as if you're evaluating a function. Other times you got to be more careful, and we'll talk about when that is in class. All right, thank you for watching.